Let's look at how elements are selected. So here, bolted pipe flange connection. So just go ahead and have a look at bolted pipe flange connections. So what you will observe from the images is that it is axisymmetric in nature, or if you look at this image, so first of all, what is axisymmetric? So which alphabets do you think are axisymmetric? Is T axisymmetric? Is I axisymmetric? And what about H? Is it axisymmetric? Is O axisymmetric? So how do you define axisymmetric? So here what you see is there are 1, 2, 3, 4, 5. So there are 8 bolts. So 360 divided by 8. How much is that? So you have bolts exactly at 8 locations. So this is not perfectly axisymmetric, but how is that they have assumed it as axisymmetric? So 22.5 into, yeah, 22.5. It is 360 divided by 8 is 45. So for every 45, it is sector symmetric. So for every 45 degrees angle, it keeps repeating. So this can be called as sector symmetric. So again, if you take the 45 degrees, you can divide it into 2. If you cut it, so it will look something like this. And here again, there is one bolt, and this is a bolt head. So why is that it is so fine in the locations where the bolt and the bolt head come in contact with the body? So here, is it too fine here? What is the necessity of having a fine mesh here? This is a different material and this is a different material. And when they come into contact, will they create some stresses? What is the reason? Why is this finely meshed? And this side is also finely meshed. And above this, again, this part is finely meshed. Is it because that there is some force acting downwards, which is very important than the bolt as such? Suppose imagine if this was a softer material, what would happen? So, do you know the concept of washer? Why do they use a washer? Here, if you use a washer, what would happen? If a washer is used, Will the stresses be spread over a region much bigger than this? So what you see here is 22.5 degrees and segment this segment, and here they have divided into two, and here they have what they have done is from two they have split using multiple nodes. They have brought in here and they have captured the fillet as well. Yeah, this looks a little better. It's a well meshed one. So these are the contact nodes. So these nodes, one, two, though there are only four elements, each element has three nodes. So what kind of element is this? Is it a quadratic element or a linear element? So can you have nodes at the midpoint called as mid nodes? These are contact nodes, and you have element B, which is much bigger, whereas element A is a smaller one. So normal stress distribution in the gasket contact surface. So where is the normal stress expected? So what kind of plot is this? We don't see any values over here. It is S22, S22. We don't see any variations. So S22 along the radial distance from 28 to 52. Which distance is this? 28 to 52. So 28 to 52 must be this distance, 105. So from here it's a region which starts from here, somewhere here until this region. So let's see what has happened to the stress S22. And what is S22? It is the normal along y direction. Normal stress, sigma yy is called as S. Instead of sigma, which we use for stress, here we use S. S and sigma both are the same. Instead of yy, we use 22. So here you can use 22.5 matrix or 45 or 90. So what is happening over here? Why is it decreasing? Is it tensile at the inner side? And as you move towards the board, it moves towards compression. So exactly here at 52, there is compressive normal stress. It is close to 80. So this is compressive because there is a negative sign. Whereas on the inner side, there is a tensile stress, which has a magnitude of 20. And what units are these? So here, this is a different problem, axisymmetric one. So let's look into some other axisymmetric problem. There is a axisymmetric threaded connection. Let's look into this. So there is a pin and a box. So this is a stress distribution. The threads after axial loading, pressure penetration on box contact surface after axial loading. So this is pressure penetration on box contact surface after axial loading. So this geometry looks like a bottle which has a thread. Maybe this we can assume as a bottle, but there is no bottom. Whereas here we can consider this maybe like a cap. Again, there's nothing at the top, but what we can see is the threaded part. So this is going to be the same for the entire region. So this is a three-dimensional cutaway view, but you can always use axisymmetric. So these are the axisymmetric elements, CAX 4 elements. So instead of taking a lot of time and solving for the entire geometry, you can just consider the axisymmetric one. Let's look if we can get one more axisymmetric. There is a circular cup. So circular cup, is it a U-shaped cup? Okay, so you're forming a cup, maybe a steel cup. What material is this? A blank, a die, and the first forming stage. So shell thickness. So here we have a nice cup. So you don't need a 3D geometry because it is perfectly symmetric. Just this shape is, sorry, deformed configuration, final configuration. So these are perfectly symmetric. If you just revolve this geometry about this axis, you can form a 3D geometry like this. So Is there any other axis? One. So axisymmetric extrusion, transient, steady state. So here we have transient backward extrusion, transient forward extrusion, steady state. So equivalent plane strain. We have the deformed mesh. You can revolve this. You can revolve this geometry. And how would it look like? Would it look like two cylinders placed one above the other? So these are different axisymmetric problems. Let's see if we can get one more. Okay, let's stop it here.